Before we take a look at the RTL Viewer, it's probably worth explaining what RTL actually is. RTL stands for Register Transfer Level. It's a design abstraction used to define digital circuits as a flow of signals between individual elements. In the past, when you've drawn out circuit schematics using things like logic gates, flip-flops, registers and wires, you've actually been drawing RTL diagrams. These diagrams are a high-level representation of the circuits they describe, as opposed to other representations such as hardware definition languages or netlists, which can be considered lower level. They're very easy to present graphically and are the prime way to describe and explain small combinational and registered digital circuits to other engineers. It's worth bearing in mind that if you were to apply for a job in digital electronics, you would be more than likely asked to draw something out in RTL, so it's definitely an acronym that you want to remember. So we're going to use Quartus' RTL Viewer to look at the RTL for our design. As I mentioned in the previous screencast, the analysis and elaboration stage of compilation determines the logic of your design by testing each module with all possible combinations of inputs and generates a netlist of gates which represent that module. By using the RTL Viewer, we can view this netlist as a digital circuit, so you need to make sure that at least the analysis and elaboration stage of compilation has taken place and has a tick next to it in the task window before you open the viewer. Remember, you can use the different compile buttons to run the compilation to progressive stages. We can open up the RTL Viewer by going to Tools, followed by Netlist Viewers, then clicking on the RTL Viewer. So the viewer has quickly appeared, showing us our design. Now, as our module is simple, the design is very simple. You can see that we have two input ports, A and B, going through an AND gate to our output. On the left-hand side, we can navigate through the different elements in our design, our gate primitives and input and output ports. As our current design is very simple, there's not an awful lot to see here, but for much larger designs, this navigation pane makes it very easy to find the parts of the circuit you're looking for. We may as well go ahead and make our design a bit more complex, with a couple of extra inputs and some more gates, and then we'll see these changes reflected in the RTL Viewer. So what I've done here is add two more inputs, C and D. I've also added a couple of wires to our design so we can connect between the gates. Wires in Verilog work similar to how they do in Jack, so just add them in like this for now. We'll come back to the syntax in the next lab session. I've made the circuit a bit more complex with some extra gates, so we'll compile this and see what we end up with. Opening up the RTL Viewer again shows us our new circuit. You can see that we now have four inputs, A, B, C and D, going to AND gates, with the outputs connected through wires to an XOR gate. It's worth noting here that each element is labelled with the name of the output wire, except for the XOR gate, which has just been labelled COM, presumably short for combinational. So as your design grows, the complexity of the RTL will increase. So as we move through the module, we'll be coming back to the RTL Viewer to look at how it represents more complex circuits. It's a good idea to use the viewer to manually verify your designs when you first write or change them, as it saves you time in the simulation phase if you know that your design is as you expect it to be.